Hello, everybody. So for our project, which is me, Ernie Lozano, and then Angelica Romero, which are both on Ernie's computer right now, did delay lock loops. And so the simplest way to put it is with the highest level up. So basically, if you have two clocks, whatever two clocks, same frequency though, for this case. If they're in any way out of phase, this delay lock loop will make sure that they get in phase. And it does this with the use of a phase detector, a charge pump that feeds a capacitor to store the value of how out of phase they are. And then that value gets fed to a delay chain, which basically takes that clock that's out of phase with a reference clock and delays it until they are in phase. And it's actually really useful because, and we'll get into it a little bit later, but with delay chain, the series of inverters down here, you can pull from different parts of this delay chain to get your same clock, but with practically any phase you want. Yeah, and so, we'll talk more about it, but take it away, Ernie.
So on Virtuos or Cadence, we have the entire project, which is the delay chain spitting out different clocks at different intervals and having the output of the final clock back into the phase detector, what Brian was saying, how the reference clock and the delay clock will be changed on compared to just checking if they're phase or not. And then within the control systems is a phase detector. So and within the phase detector, we have a SR latch, a NAND version. So therefore, this is active low instead of the XOR like we learned in 133. And we have the reset coming out from both the reference clock and the output of the delay chains to reference itself. So I believe there is a simulation, if I can find it. Yep. Clock 1 would be the reference clock, clock 2 would be the output clock. And so we have the reference clock leading the delay chain, meaning that we have to charge the capacitor. Q1 would mean charging, Q2 would be discharging. Therefore, if Q1 is bigger, it would charge the capacitor more. And from looking at the reference clock, we have big pulses, and it would be bad if the active low were to be clock 1 and clock 2 to be 0, 0, meaning the forbidden state. Therefore, within the delay chain, we have a pulse taper, which is a monostable, pretty much getting that whole pull down width down to just a nanosecond, therefore not overlapping into the forbidden state. Next is going into the charge pump. The charge pump is literally just a PMOS allowing current to flow, charging the capacitor, and NMOS allowing current to flow to ground, discharging the capacitor, feeding into the delay chains, whether or not to feed current to switch faster or to pump current to discharge current to switch slower. And for the final stage is pretty much getting that voltage control in for the NMOS and converting it into PMOS. And literally, this is just a CMOS inverter, but the only significance of this is the diode mode operated PMOS, which pretty much it does the same thing, but instead of having the gate voltage be one input, it's fed through itself. So NMOS dictates what PMOS does due to the current mode operated. And I think we have a simulation for that as well right here. So as NMOS increases, CMOS would decrease, or the feed control P would decrease just because as a CMOS operation. And then finally, for the delay chains, as Brian said, it takes 20 inversions of the specific CMOS that we tailored to produce one clock out. So we have 20 inversion or CMOS inversions. Never mind, it's going bad. All right, so back to it. You can see that it has 10 with inversion or CMOS inverters within here. Counting it, And within each individual block, you can see here are the starving transistors, whether it's PMOS or the NMOS. And here is the final, never mind. It's going well, Brian. It's going well. Here's the CMOS where instead of pulling up to 2 volts or down to ground, it has a signal coming from, and that signal is coming from um, the starving transistors, whether it's going to feed current more or not, to slow down the switching speed or speed up the switching speed. And again, the V control P and V control N comes from the top system, from the phase detector, control charge pump, and control voltage. And for the final simulation, we could see that from the reference clock, we could see that it's like a staircase down where the rising edge would fall into the next rising edge, delaying the clock system. And to get a better view of the control voltages, we could see that at the instance of initialization, which P control P at 2 volts and P control N at 0, then we could see that as it's charged, it's pumping out more current in through the transistors, allowing it to switch faster until it hits a steady space. And Brian, do you want to talk about your control systems if I could get out of here?
Yeah. So, and another way to look at this system, and this is super handy. Another way to look at it is with a control system, because it is there's feedback, and so this is the charge pump that we all know and love, and we've gotten to know and love for a while. But basically, what feeds this charge pump is the phase detector, and so the phase detector takes these 2 clocks, and depending on how out of phase they are, they're going to either charge this capacitor or discharge it. And so that's what the phase detector does. And this capacitor holds the value, indicating how out of phase they are. This value then goes to the delay chain to indicate how much current should flow through it, to add more delay or take away some delay, to ensure that both clocks are in phase. And so here's basically a delay lock loop control system in all of its glory. So over here you have the phase detector that I indicated in green, and it basically takes the phase difference, or the delta T, another way to represent it, and based off of that, it feeds it to this charge pump that I just showed the schematic of, and based on, again, how out of phase they are, that voltage will get stored on that capacitor, and then that value will get fed into this delay line that will change the delay for each transistor. And then you get your output clock, this gets fed back, get an error signal, and the whole process repeats. So I actually did a few simulations just to show how systems like this can be unstable and model idealities and non-idealities. So super briefly, this is with parasitics, but this is the Bodhi plot. We were working at like 1 megahertz, so nothing to worry about here. Step response for no parasitics, so an ideal case, we get something around 0.3 for a rise time with the capacitance we chose on the charge pump. And then our system is super stable in the left plane of the S parameters plane. And so that's great. But if we add a little bit of parasitics, just a few, we start to get a slower step response, which makes sense. And we also get a control system that's a little bit more closer to unstable, as indicated by this pole and 0, very close to the origin. Last thing, the way I model these parasitics is with this. This is our charge pump capacitor, and these are some parasitic components. Yeah, so thank you for watching. Have a good day, everybody. Bye.